In the previous video on stable matching problem, we have seen that we would need a little bit, something that is a little bit more general than the element constraint. We would need an element constraint that is able to index an array of variables. And for that constraint, we will introduce a hybrid consistency filtering algorithm. Not really domain consistent, not really bound consistent, but something in between, a little bit like for the two-dimensional element constraint that we have seen. Let's start first with the signature of the constraint. So the only thing that has changed in the signature of the constraint is this part. As you see, instead of an array of Java integer, we have an array of CP integer variables there. The index variable is still a variable, and the target variable z is still a variable, and this is posting the constraint that at the index y, you should have the value z. Okay, so that's for the element constraint that we are interested in. How to propagate this constraint efficiently? We have two possibilities. We have the domain consistent filtering, and we have the relaxed domain consistency filtering. And the relaxed domain consistency, what we mean there is that we will assume a range domain for the domain of the variable z, but also for all the variables in the array t, but not for the variable y. This, therefore, it's a kind of relaxed consistency. It's not fully bound consistency because we are still creating holes possibly in the domain of the variable y. So that's the small example that I will introduce, that I will use to introduce the filtering. So we have here the array T of variables, and for each entry of this array, you have the domains that are represented here. Okay, so that's all the possible values there, and the values are put in front of the corresponding value in the domain of the variable z from 1 to 9. Okay, so this is what you have there. For the index variable, the variable y, you have the values 0, 1, 2, and 3, and they are represented there. In green, it means that the value is in the domain, and if it is not highlighted in green, it means that it's not part of the domain initially. So that's the initial situation there that we have. What can we remove? Which are the inconsistent values? To answer that question, we need to do the propagation, so the filtering algorithm, and we will do it in every possible direction. As you will see, there are 3 possible directions for the reason. Let's start with the first direction. It's we will, of course, start because we are doing a kind of relaxed domain consistency. We will assume that the domain of T and Z are ranges. And so I have used the green color, but it's a light green color to say that I consider that these values are part of the domain when I will do the filtering, so that I can really reason on bounds. So you see that instead of the value 1 and 3, I've got the values 1 to 3 for the first variable in T. Okay, and this is why this value is part of the domain as well. Okay, that's the same for the domain of variable z. You see that 5 is now included in it because I consider that it's the range from 4 up to 7. 4 up to 7. Okay, so the first direction of the filtering is I will filter from T and Z in the direction of Y. So the goal there is to prune the domain of the variable Y and remove the values that are possibly not part of the solution. And that's my filtering rule. So what I will do is that I will do the following rule. I will intersect the domain of Z and the domain of the corresponding entry T of I, the variable at T of I. If I see that the intersection is empty, I can remove the value I from the domain of Y. Okay, but let's not forget that we have relaxed the domains. So computing the intersection here between two ranges is easy. It's easily done because we assume that it's interval domains. We can easily do that in constant time. Okay. So let's start with the first variable there. So I want to intersect the domain of T0 with the domain of Z, okay, in the relaxed form. As you see, there is no intersection there, okay? Since there is no intersection, I can remove this value 0 from the domain of Y, okay? I can remove this value 0. Okay, I consider the next variable, and I intersect again the set of values there that are green with the set of values there. Again, the intersection is empty, so I can remove that value 1 from the domain of Y. I can remove this value 1. The next one, the intersection is not empty. You see that the intersection here contains at least four values, so I cannot remove this value 2. But it's already not part of the domain anyway. So, but for the index 3, if I intersect this and this, the intersection will contain the 3 values there. Okay, it will contain this value, and this value, if you project it. And therefore, we cannot remove the value 3. It's still part of the domain. So after this first direction of filtering, I have removed the value 0 and 1 from the domain of the variable y. Okay. The other possible direction in terms of filtering is to filter from t and y in the direction of z. And that's the filtering rule that I will use. I will simply take among all the possible values, I will take the minimum in the domains and the maximum of the domains for every value that is still part of the domain of y, for every still valid possible index value in the domain of y. The only possible one here is this one. That's the only value that remains. So I take the minimum, that's this one. The maximum, the minimum is this one, the maximum is this one. Okay, so the minimum of z will be updated. Well, I cannot really update it, it's still 4. And the maximum, I will update it to 6 because that's the only possible index left. Okay, basically this part is not in the domain anymore. And so if you project it, you see that the largest value there is 6. And so I update the domain of z to 6. Okay, and the last possible direction is to filter from z and y in the direction of t. We are lucky here because we can only do something if we realize that there is only one value left in the domain of y. And that's the case here, okay? We are in the case where we have only one value left, that's the value 3, okay? So the domain of y is equal to 1. And therefore, I perfectly know which index will be used here in my relation. I know that the index is known, it's index 3. And so I have an equality between the variable at that index and z. So I will force the equality between the domain of z and this variable there. And so I can remove here the 3 values from the domain of t3. Okay, because they need to be equal, so these ones should be removed. Okay, and again, it's very important to notice that we can only filter a ti variable under the condition that the domain of the variable y is as a size of 1. This is really a relaxed consistency. And to realize that it's a relaxed consistency, it's not able to detect any possible failure, for instance. I have shown here, I have depicted an example of domains for that constraint that is inconsistent. So there is no feasible solution even for that constraint, but the relaxed domain consistency that we have used will not detect it. But we can make the exercise of detecting it. As you can see, the domain here of that variable with z is there is no common value there. Okay, so clearly the value 0 should be removed. That's the same here. You see that there is no possible intersection. Okay, if you this value is part of the domain of t1, but it's not part of the domain of z. So that one should also be removed. For the same reason, that one can be removed and that one can be removed. It means that we would, with a domain consistent filtering, we would remove all the values from the domain of y. Okay. And so we would detect here that there is no solution. This is exactly the reasoning that we will do in the next video.